let's invite Professor Chandru to give the first inaugural prestigious lecture, Ravi Kirloskar lecture. Thank you very much.
Thank you. I just want to check the microphone. Yeah, I'm audible. By the way, I don't look anything like that picture. It was taken, I guess, around the time you were president, Hari. So, yeah, so after that introduction, comes the anticlimax, but no, I'm very honored to be here and also to be giving this lecture in this new series named after Ravi L. Kirloskar. Of course, several of the Kirloskar family members are good friends, and MIT was mentioned. Vikram was an undergraduate at the time. I was a PhD student, so I've been close to the family for a while. Yeah. So I think I can skip this. Just want to say that I think we've all been fortunate to live in an extraordinary time, right? I think it's a little bit tongue-in-cheek there, but about numerically, most of human history was boring. But the fact is that exciting things happened, I guess, with the Industrial Revolution, right? And since then, it's just been pretty much a singularity, right? We've been riding a singularity in one way or another, and I think officially, I think we are in a cognitive age now. And around 2005, if you recall, Fairchild Semiconductors was set up around 1958, right? So if you look at the doubling that Moore's law represents and double it 32 times, which is half of the chessboard, then around 2005 is when you get into the second half of the chessboard. And that's when the magic starts, right? So I think we are so fortunate that we've had this exponential technology that we've been able to live with and get such an amazing ride through this modern historical age, right? So I did study in Pilani. I think I spent more time on the cricket fields than in class, but we had a great time. Pilani Electrical Engineering was considered one of the stronger programs in the country at the time, and it was good fortune to be there. By the way, I used to bowl outswingers, so I'm was considered the booby of BIT's team in those days. And the guy next to me, Arun Tikku, used to bowl the in-swingers. So we were the two swing bowlers. And so we used to have a lot of fun. So that's the electrical engineering degree. And this is what the campus now looks like. It's really quite beautiful. I was there for I gave the convocation address a few years back. So I took the picture then. So historically, I think decision sciences and operations research was part of it. I think in many ways AI was also one corner. We were all within that framework. Intelligent control, cybernetics, all of these were essentially part of what this field was based on. Of course, as always, we start with Turing. But little later, I will tell you why history should go further back. But this was about where, I was getting serious, right? Just graduated from BITS Pilani and going to graduate school and so on. And computing, was starting to drive the translation of mathematics in many ways. So I ended up at MIT and worked in fairly abstract computational mathematics. I was Ralph Gomery, who was then the head of IBM research at Watson, had defined a field of using abelian group theory to describe discrete optimization problems. My PhD advisor, Jerry Shapiro, had followed up on Ralph Gomery's work. So I ended up doing my PhD thesis on these group optimization problems. And Ravi Kannan had arrived as a young faculty member. And so we collaborated on various aspects of complexity. And in those days, he was an operations research guy. His PhD was in operations research from Cornell. And Tom McNanty, of course, was my other mentor. So with that, the first innings begins, which is basically sort of the academic journey. And in your first innings, you want to bat with a straight bat, right? And so that's why Gavaskar and Dravid are the epitome of straight batsman, because you're finishing your PhD and coming into was that he was a mathematical philosopher. Okay, great. So Leibniz was the one who actually saw that essentially symbolic reasoning and computation, arithmetic computation, are really two sides of the same coin, right? And so really you can think of him as the founder of what is today called neurosymbolic reasoning, right? And and of course, this famous quote by Russell of a translation of Leibniz's right, as if philosophers don't need to argue anymore, they just need to compute, right? And they can arrive at the solution. So which kind of points to the fact that reasoning is actually a computational issue, right? And surprisingly, later on, I got to know through the writings of Professor Roddam Narasimha, who became kind of a mentor for me, that classical Indian science was also essentially driven by this idea of computation as the foundation for reasoning. And of course, he called it computational positivism. And he used this little shloka, which was Drik plus Ganita equals Siddhanta. And so that is, in a way, going back to the same principle that computation can drive intelligence, right? And so I began, I was trained in operations research, linear, integer programming, all of these areas. And I started trying to see how this connected with reasoning, right? And no, as you can see, there was, you could actually reason with linear inequalities. Linear equations, of course, all of us know. With Gaussian elimination, one can address linear equations. But Fourier pointed out that you could also do this with linear inequalities. And essentially, it's when you eliminate a variable, you're taking the shadow or projecting one dimension. And so if you start with a polyhedron and you keep dropping variables, eliminating them, you'll eventually either end up with nothing or you'll end up with a line segment. If there's a line segment, it means the polyhedron was real. If it is nothing, it means the polyhedron was empty to begin with, right? So it's a very nice, simple geometric way of thinking about things. Resolution is really variable elimination on propositional formulae, right? And so you think of again, essentially cancellation, right? You can cancel a negation with a positive proposition, and you arrive at the resolvent. And so it's a very similar idea, right? And when you're dealing with solving over the integers, it's a lot like solving over the reals. Just like you solve with Gaussian elimination, here too you can triangulate your integer matrices using what are called Hermite normal forms and Smith normal forms. And Ravi Kannan was the guy who proved that you could compute all this in polynomial time, right? So, it was, all this was falling in place and coming together when I had just started at Purdue and I was thinking about what to do next, right? And then I was fortunate that somebody told me, this goes beyond linear systems. You can actually do nonlinear reasoning as well. And I said, how do I find out about it? They said there's this very powerful mathematician at Purdue. He's a bit eccentric, but you can you can go and ask him, and he will tell you all about it. So his name was Sri Ram Abhyankar, and so Ram, as we called him, Ram was only too happy to teach this to scientists and engineers, because he said, I've always used elimination as a proof technique. So he proved all these major results. In fact, some of his papers would be the entire volume of the American Math Society Bulletin, right? Which would be one long algorithmic proof to come up with some very deep theorem in algebraic geometry, which otherwise, people would use commutative algebras and so on and make it unnecessarily difficult. He just would use first principles of elimination. So we became his students, and I had the good fortune of writing some papers with him. And of course, we became the students, we became the scribes. This led to a very nice book, which is actually the bestseller for American Math Society. Right? It's a monograph that says algebraic geometry for scientists and engineers. Anyway, so I went on to keep working on this idea of reasoning and reasoning using various types of resolution. Resolution is that elimination technique, right? And it was important to know on what types of formulas this resolution works better than on others, right? It turns out that there are these formulas that are called Horn formulas, where you have antecedents, but a consequent can only be one letter or none, right? So if the consequence is restricted to one letter, that's called a Horn rule. So it says this and this and this and this implies Y1, right? Is a Horn formula. Now, if you have a string of these Horn formulae, then you can, or you're essentially looking at a conjunction of the formulae, then you can determines satisfiability of the entire system. That is there a truth assignment, true-false assignment to all the variables that makes the entire formula true? That's satisfiability. That can be resolved in linear time using chaining arguments. And these chaining arguments are modus tollens and modus ponens. So this was a, if you remember in the early 80s, people were building expert systems. They were all based on Horn formulae because chaining, made it easy to build expert systems. So then for the next few years, like all young academics, you have to build a career around something. So my career was built around finding all kinds of special structures of formulae that could be solved very, very efficiently like the Horn formulae, and showed that, this, I think you mentioned Jay Chandran, right? So Jay Chandran came up with one of those results. I think we were scooped by Knut, which is not a bad, turn of events, but it, he did this work independently as well. So, so there were a whole bunch of papers that came out of it, and eventually we wrote a book. So John Hooker was an interesting guy. He was a philosopher who did his PhD in philosophy and then decided to study operations research and did a second PhD. And so John and I became good friends, and our writing styles were similar. So we said, okay, let's also write a book together. So we, this led to a series of papers and then eventually a book. We jokingly tried to tell John Wiley and Sons that we wanted to name the book Eating Sauerkraut with Chopsticks, right? And of course, Wiley refused. They made us choose a very staid title, optimization methods for logical inference. But the first line of the book starts with solving logical inference problems with optimization methods is like eating sauerkraut with chopsticks, right? So we did slip it in the book. Right? There were several other actors involved. Bob Gerslow, who unfortunately died very young, and Jean-Louis Lasset, who was my mentor at IBM, at Watson. I used to be a summer academic visitor at Watson, and we wrote some papers on constraint logic programming over the reals and so on. So he was a real logician. He was a student of Richard Bucke, right? So the original Bucke automata man. So then I come back to India, and as Naredi says, come to the Department of Computer Science and Optimization, and find out the first time, while walking up to this faculty hall, that there's a statue of the Maharaja there, and there is a sense that the Maharaja had been very magnanimous in creating this institution. In fact, I think the Queen Regent's jewelry was given to complete this building. So of course, we all consider J.N. Tata as the original sort of person who conceptualized this institution, but we also benefited from the magnanimity of the royal family, and private philanthropy has been actually there at the roots of this institution. And it's interesting to see that now it's come a full circle, and we're again looking at private philanthropy at Center for Brain Research or the new hospital medical school. A lot of it is coming again from that. But you have to remember that there was a promise made that we would somehow increase the material wealth of this state, this country, etc., and that was the intent. I came back, and one of the first things that happened was, I think, and if you recall, I think somebody sent a message from G.N. Ramachandran's family saying he wants to meet someone who works in logic and computation. So I started meeting the famous biophysicist, crystallographer of one of the greatest this country has produced. In fact, it's a real tragedy he wasn't given the Nobel Prize. Right? And GNR he was already struggling a bit with Parkinson's, but he had written up a lot of papers, and I started interacting with him. And what I realized he was trying to do, and Apurva, you will like this, he was trying to build reversible circuits. And he called them Boolean vector matrix formalisms. And these reversible circuits he saw as kind of the foundation for quantum computing. He didn't call it that, right? But his idea was that in order to actually understand at a molecular level or intracellular level what happens in biology, you actually need a new computing paradigm. And the genius of the man was that he was starting to work on it on his own. Unfortunately, I think the Parkinson's and so on slowed him down, and he wasn't able to get far enough. But basically the same idea that Feynman had, right? That essentially to compute physical phenomena at that level, at that nano scale, you would actually need a different type of computing engine, right? And so this was my first idea that first time I realized that, you know, there's something going on between biology and computing that's kind of interesting, right? And one should look at it more, right? So, but anyway, I was deep into this, you know, reasoning and automated theorem proving. And so we went, but what happened was after coming to India, I didn't want to do that much foundational work anymore. I wanted to actually build systems, right? And so I had a lot of good experiences, including at CARE, at the Center for AI and Robotics, building, you know, expert system shells with Professor Vinay, who was then a PhD student, and then later on with students at CSA, we built the CARE IISc Prologue, and also built concurrent Prologue on the Param machine here on campus, but I continue to do some mathematical work as well with Vivek Borkar and Professor Sanjay Mitter, and of course, as I was mentioning, with the IBM folks. Suddenly, around the early 90s, when we were doing all this work at CARE, Professor Vidyasagar, who was then the director, wanted to prove some convergence theorem on recurrent Hopfield nets, right? And so we were working on proving those convergence results, and Professor Vinay Vidyasagar and I worked on those problems. And then Vinay and I realized that there's actually a nice little optimization problem that you could solve to actually pick optimal weights, synaptic weights for these Hopfield nets and get optimal performance out of it. And this actually was a very powerful result that we came up with, and a computational engine to prove that you could actually get fully optimal, you could train the Hopfield net to optimality, to provable optimality using a mathematical construct. I remember, I think, presenting this at the 25th Silver Jubilee of CSA department, and Tom Kailath was here. And Tom said, you know, this is a remarkable result, and he and his student Bhavani Roy Chowdhury were working on neural networks at that time. And, you know, in many ways, and of course, this was presented at SODA, which is the Symposium on Discrete Algorithms, of an ACM SIAM meeting. And I think we were at the forefront, right, in training neural networks. And so, you'll see a series of missed opportunities, but this was one of them, right? We could have been like University of Toronto, right? If we really sort of wanted to push this. Actually, one of the extraordinary colleagues was Satyakirti, who then took this optimization algorithm that we had built for this problem and adapted it as the kernel method for support vector machines, and actually made a huge name for himself building those kernel methods. So these are all at the foundations of machine learning in one way or another. So then this idea that biology and computing have something to do with each other keeps creeping up, right? So around mid-90s, this book comes out called Out of Control. Some of you may recognize the name. Kevin Kelly was the founder, editor of the Wired magazine, right? So I used to read the Wired regularly. So it was, when he wrote this book, he got very excited about it. But again, he was saying that somehow the life and machines, are similar, and eventually everything is going to look more biological, right? And so that became a theme. Professor Vinay, who had by then graduated and joined our faculty, he went away for a while to math science in Chennai and then came back. He pointed out something quite remarkable to me. He said, if you look at the timeline of molecular biology particularly, and modern computing and information science, they're remarkably concurrent, right? That was a comment he made, and then so I actually went and sort of tried to lay out this timeline, and one could see that there was remarkable sort of concurrency going on, and there was exchange of ideas going back and forth, right? And so really felt that it was worthwhile then jumping into computational biology, and that was in the mid-90s. I think the Jawaharlal Nehru Center here used to fund us to do meetings, right? So we pulled together an international meeting where we brought computational biologists and computational biologists from all over the world, and sort of launched a program in computational biology, which gradually led to some ideas that later on became strand genomics. Right? Meanwhile, what's happening in computation is that we're turning the curve, right? Now we are getting close to the year 2000, and so basically we are getting to the second half, right, of the chessboard. So 32 squares have been filled, and so it's starting to turn up, right? And so you realize that something big is coming down the pike, right? We look at how information becomes a fundamental aspect of development. And the thing that stands out is everyone talks about sustainability, but no one talks about equity. So how do you actually bring equity into the equation when you think about this whole wave of information technology? The other thing that really stood out is India was making great claims of moving into the information age, but we hadn't built a computer after TIFRAC, computer from scratch. Right? Lots of people had assembled computers, but no one had actually built a computer from scratch. after the TIFR automatic calculator was done in the late 50s. So we set about that idea of maybe building a computer from scratch. And obviously, at this point, we wanted to do it with a different concept. And that took us to mobile computing, but we'll get there. A point I want to make here is that when you want to think about impact and you're in academia, there are many quadrants that you can move into. You can move into the Bohr quadrant, which means that you do extraordinary theoretical work and you make a huge mark by pushing the frontiers of knowledge. You can take the Edison corner, which is prolific in invention. Maybe not using breakthrough knowledge, but building lots and lots of solutions. Very valuable, right? All corners are valuable here. But the extraordinary corner to get into is the Pasteur quadrant, because you're going up in knowledge and utility, right? And so this is something to keep in mind when we all talk about academics getting into innovation. It's Pasteur's quadrant that you want to be in, right? Because you have the wherewithal to push the frontiers of knowledge, and you want to have impact, so it has to have utility. So what you want to do is utility-inspired basic research, right? So start with the problem, okay? Don't start with the technique that you know how to use. No. So that's the second innings, right? And so now you can be a little more cavalier, right? It can be a Kapil with a long bat, or a Gary Sobers hooking to the fence and so forth, right? So this is where, as Narahari pointed out, Percolat came together. NV was the chairman, and he very kindly, gave us a nice space on the ground floor called which we called the Perceptual Computing Lab. And of course, NV's vision was we should have something like a media lab within our department, so in computer science. And so that's what we did. We started a lab where the four of us got involved in building stuff, all kinds of new demos. And it'll take an hour to describe everything we did, but the interesting thing was that at some point, this lab became ready to launch into the real world, right? And the person who sort of opened the door for us was Mr. Ratan Tata, because he came as the president of the court in 1999, it was, I think, 99 March. And he announced here, in fact, that, why aren't there more startups? Right? So that evening, Swami Manohar, with a little prompting from all of us, penned a note to, I think, Professor Govardhan Mehta was the director then, saying, as a lab, we are ready to launch companies. What are the institute rules? So the response came, there aren't any rules, but we'll appoint a committee. Right? So from 99 till 2000, there were committee deliberations on how to allow this entrepreneurship thing to go forward. October 20th, I think, of 2000, the council voted to permit faculty entrepreneurship. And so two companies were born. One was around the computer, and the other was Strand. We'll say more about them in a minute, but it was the first time something like this was happening in the country, right? And fortunate for us, we had Professor H.P. Kincha, who was running SIDE, and Professor Kincha helped us structure it. We also got a lot of advice from one of my old classmates at MIT who had become the head of tech transfer at Harvard. And so he suggested how we should structure it and the negotiations and so on. And we brought in a young lawyer, Rahul Mathan, to actually help us with the whole exercise. And Rahul pointed out to the institute that if the institute held less than 10% equity in the startups, there would be no liability, right? And so the institute then figured the right thing to do is for it to take 9.8% or 9.9% in the companies, and that's how we got started. Okay? And that 9.9% was justified as sort of the prior work done in the institute, which was being taken into the companies and so forth, right? So, and then various things happened. We also had a startup called Manjara that was, and there were no incubators then, right? So we had to build our own incubator. So we went out to, in Sadashiv Nagar, we rented space and built our incubator. And Manjara got acquired very early by Google as soon as it was built. It was a new clustering engine for search. And how am I doing for time? 15 minutes, oh, pretty good. Yeah, yeah. So Manjara was acquired by Google, and then we kept building Picopita and Strand. So let me just say a little bit about Simputer and the company Picopita. The Simputer itself was conceived, I think around 1998. We were thinking about how to bring equity into the information age in the context of India. And we thought something like a little transistor radio that could go anywhere, that could be shared. People could look at these kids, right? They were very happy to share a computer, you know, the earphones, you know, one for each of them. They're sharing, and they're playing around with a computer. This was enabled. Simputer actually stood for Simple, Inexpensive, Multilingual People's Computer, right? So we had to enable it in, of course, Indian languages, and we went on to do a few other things, but it could speak to you. So for people who were semi-literate, if there was text information, it could be converted into speech. And Ramesh wrote an extraordinary engine called Dhvani, which actually could speak in Kannada and Malayalam and Hindi, and so and he made it open source. So it's still out there somewhere. And so I used to find him at 3 a.m. in CSA in his office, recording primordial sounds, and then doing digital signal processing with it, just to, you know, so he created sort of a library of sounds and then figured out how to put them together and to make it sound more natural in specific languages. So extraordinary effort. And we were doing all this after classes, you know, in the evenings. So we became big customers of the tea shop, which was right opposite CSA, right? So samosas and chikki and tea keep working through the night, right? So we went on to then build 10 prototypes, which we launched in 2001, and then started refining the prototypes and created a company called Picopeta Computers, and this attracted a lot of attention, right? It was the first handheld built to run the entire Linux kernel. It was built on a strong ARM chip, It was a 7-layer motherboard that we had designed and fabricated ourselves and debugged. It was not an easy job debugging that 7-layer motherboard. And so it got some attention, right? It became BBC, Click Online or whatever. They came and interviewed us. The New York Times declared this the innovation of 2001. And even Technology Review rated us as one of the hottest startups of that time, right? But India had no venture capital at that point. We had no risk takers who were willing to put the kind of money needed to do something like the computer. And the, for example, we had fully integrated it with the Reliance phone, and we had even got GPRS into the computer. We had integrated it. It could have been the first smartphone in the world, right? Because we were about 5 years ahead of Apple or Samsung or whatever. It needed probably $20 million, right? To be fair, that was a lot of money in those days, and it was not easy to convince people to put that kind of money up. So we did what we could. We made about 20,000 pieces. Then it evolved into something called the Geo Amida, and they made another 20,000 pieces, and it at least introduced the meme or the idea that mobile was the future, right? And so when smartphones actually arrived, we were kind of prepared, and we knew how to leverage. Of course, MHRD was very happy, right? This was declared as one of the top 5 achievements of the NDA government. But no money, right? So that was difficult, but they did give us awards. So we got the first Devang Mehta Award for IT innovation, and this was sort of the blurb that it has the potential to put computing power in the hands of the masses, right? And of course, the New York Times said that this is how computing would look if Gandhi had invented it and Steve Jobs had done the marketing. So that was kind of an interesting phase, right? So my own journey, went with the computer for a while, but then I focused more on building Strand. So the way we did it was Ramesh and I said, we'll run Strand. And Vinay and Manohar said that they'll run this computer company. And so because you needed to actively engage. And Strand was basically built out of this idea that biology was becoming very data-driven. And so it needed new types of data analytics. Physical sciences had MATLAB, which was great. Right? Life sciences required something a little different because there's no underlying equations, right? That like you have with physical sciences. So we needed to be able to do exploratory data analysis. We needed machine learning to be able to, understand what the data was saying. And so essentially Strand built that first platform for the life sciences. We called it AVADIS. It was access, visualize, analyze to discover, right? So it was, you had to access data from all these different experimental instruments and so on. Much of it had to be clean because it's never clean. And then you had to visualize the data. It's high-dimensional data. So you needed special types of visualization tools. And you needed visualize, analyze. So we compiled R into the platform. So you could run any R script from anywhere inside the platform. And discover, we built a natural language processing engine called Grammatica to actually read all of PubMed. all of Medline. And we built internal knowledge graphs to be able to interpret results from what we saw from the data. Now, this is all done between the period 2001 to 2004, roughly. And no deep learning, no GPUs, right? But actually India's first AI company, right? And this goes on to capture. Now, the one smart thing I think we did was we decided we're not good guys to build a sales force, right? So we said, let's find channel partners. So we went to Agilent, we went to Illumina, we went to, at that time there was a company called Strategene, which later got acquired by Agilent. And Agilent put up its hand and said, we'll be your global distribution partner. But we have our brands called GeneSpring and so on. So we'll put Avadis in, and it'll be an Intel inside strategy. So we'll do our branding, but you'll get a share, right? And so that's how we built the company. We became the Intel inside for bioinformatics products around the world. And if you look at the citations, it's somewhere around 35,000 citations. So in terms of impact, I think on the scientific community, particularly the molecular biology community, that's how I would measure impact, right? Then we suddenly realized that there's an opportunity to get into actually clinical work, right? Because we've done the hard part of analyzing and building the data tools. Now, if we could add a lab, then we could become sort of the clinical, diagnostics company for the new age of precision medicine and so forth. So that's what we did. Because something special was happening by about 2010-11, we saw the first application of whole genome sequencing to cure a little boy called Nick Volker. And Howard Jacob, the clinician, the medical geneticist who was treating this child, is the one who came up with the diagnosis, and Nick is now a college student and he's doing well. I spoke to his mother a couple of years back. And so Ramesh and I were in the audience listening to Howard Jacob tell this story. And we said, we have to do this in India, right? So we came back. And around the same time also, Angelina Jolie comes out with her story about how she brought her risk of breast and ovarian cancer from 87% to under 2% because she tested her BRCA mutations and then took some corrective steps, right? And so this actually opened up the whole field of clinical genomics in the US and by osmosis in India as well. It was starting to happen. And we were starting to treat thousands of patients, right? I'm sorry, we were not treating them. We were diagnosing them. And we were diagnosing the mutations in the tumor, in the tissue, and advising the physicians on what options there were for treatment through our reports. And that was the clinical impact of STRAND, right? That was starting to happen. By the way, Dimple Bawa is kind of the Angelina Jolie of India. She was the one who really got people to think about the risks of breast and ovarian cancer and the BRCA mutations. There are actually about 19 genes that are responsible, which you have to look at. So you really need a next generation sequencing approach to this, right? So there are tons of stories to tell, but now on the financial side, right? just, I mean, we were all quite happy with just impact on research publications and, saving a few patients and the good stories there. But, you've raised investments at various points and you have to return to the investors, right? So essentially, we had raised about $6 million in the early stages. Of course, some grants and some soft loans from TDB and Nimitli and others. We had raised another round of 12 million to essentially build the labs and create the laboratories. And then we raised a third round of 10 million to essentially start working with pathology and pathology labs and so on. And I think we were poised for scale at 2021. By then, everything was in place, it was running, the reputation was there, and at which point we were approached by Reliance, who had been told that genomics is, getting to a point of democratization because of something like Moore's law, and we'll just see what that is. And this is the right time to invest into this field, right? They gave a good exit to all our investors, so I could sleep at night. But see what the market did when they announced that they had acquired Strand. The market gave them a lift of 3.83% in their stock on the announcement, which, given their market cap, amounts to $8.1 billion. Okay? So IISc will never say this, that they created a unicorn, right? But the impact is that of a unicorn, right? And they, it's an impact to the national economy. And if you want to think about how we go about getting to Viksit Bharat, you leveraging our academic strengths. This is what we do. We innovate, and then we embed it in commercial partners who know how to scale. And then the market gives value because, as academics, we don't know how to scale, right? I've been watching how Reliance goes about it for the last 4 years, and it's something that we will, it'll take generations to learn, right? So I do think this is a story that's very repeatable, right? It just has to be thought through and repeated. I was saying that there's a Moore's law in genomics. It's actually even faster than Moore's law. Around 2006, 2007, Shankar at the University of Cambridge comes up with this idea of next generation sequencing, builds a machine called Solexa. And Solexa is sold to Illumina. And then you see this drop. So it's moving at the square of Moore's law, right? And around here, it talks, it's about $100 million to do the first human genome sequences. And where is it today? It's $150, right? So from $100 million, it's come to $150. Today, with GeneMind, MGI, you can do it at $150. Illumina is still holding out, charging about $250, but it'll have to compete, so it'll come down. This is the big new Illumina machine. It's phenomenal capacity, but the Chinese machines are also getting very, very good, right? So anyway, this is, we are heading towards the $1 per gigabase number, right? Which is the tipping point, at which point you can do all kinds of things. Of course, Strand is putting out all kinds of new products, and so watch the space. I think there's a fun product called NutriDNA, which I would recommend people use because it kind of tells you what foods are good for you based on your genetic markers. Very quickly then, just to point out that around 2011, after 10 years of the first human genome sequence having been read, Eric Lander says we must learn to program cells with the same facility with which we program computers. And almost by cue, these two young chemists, actually, I think Emmanuel Charpentier is a microbiologist and Jennifer Doudna is a chemist. They come up with this technique called CRISPR, which is a defense mechanism built into bacteria, where when it recognizes an attacking virus because it has stored a certain palindrome in its DNA, which recognizes that the virus has come to attack, and it sends out a guide to go and attach to the virus and an enzyme that will cut up the virus, right? So it's a match and cut, right? And that, it turns out, is a tool that can be developed for general use, right? And that's what Doudna and Charpentier discover, and gets them the Nobel Prize in 8 years. I think it's pretty much a record, right? So within 8 years. I was going to show you videos just to give you a quick sense. This is actually an actual CRISPR mechanism at work with an electron microscope. So you can actually see it cleaving, right? The nucleic strand. It sometimes takes over a minute, sometimes takes 20 seconds. They're not able to predict very well. And perhaps if we had quantum computing, we could, right? Because these are kind of nanoscale energy calculations which we need to take. The other thing that it does is when it matches, there's a different type of enzyme which will now cleave any nucleic material inside. So you can put in nucleic material or reporters with fluorescent tags, and you know that it has found the match. So it's a detection mechanism that can be used for diagnostics. So that's what I couldn't stop after a strand, right? So I had to set up another company, and CRISPR Bits is this company. And all the founders are alumni of Bits, my contemporaries. And so an electrical engineer, Rajiv Kohli, who's now a professor at Columbia. And so we set up this company, and we are now building platforms for CRISPR. Lots of products now just hitting the market, sickle, typhoid, AMR, so antimicrobial resistance, testing food for safety, and for animal health, checking for viruses and so on. Ultimately, I think there's an electrowetting problem here. It would be really cool to create a microfluidic chip which has both got digital and microfluidics, and actually do multiplexed CRISPR assays, which would be completely point of care. And this is a 5-year horizon problem, but it can be done. Just want to end by saying that we've had a great run with digital technology. I think it's turned a corner, and now we are in the age of living machines. And I think there's a lot of interesting work to be done in biology, particularly with all these tools we have. In particular, I was very interested in the idea of how we get to universal healthcare, and around the pandemic, I guess most of us felt that there were challenges, and we really need to think about how India, if you want to be Viksit, is also Swasth, right? Because without health, we can't be Viksit. So how do we get there? Of course, Kailash Satyarthi said, we simply have to make a constitutional fundamental right to health, right? And that from that many things will flow. That's one way to approach it, but there are several ways. And so a bunch of us got together and set up something called the Lancet Commission for citizen-centered health systems for India. It took us 5 years. The report is now ready. It was published in January. And I think there's phenomenal opportunity for electrical biomedical engineers to now jump into this health space. As you know, I mean, every day there's a conference that talks about how AI and medtech and so on are going to change the future of health. So this is probably my last journey into doing something in universal healthcare. Just want to end with pointing out that we've all gone through the Negroponte journey of being digital, right? His famous book, right, which talked about it. But I think what's special about what we can be in India is we can be digital and be Gandhian, right? And I think if we can pull that off, I think we'll create a new model. We don't have to do everything Silicon Valley does, right? We can do some things differently. And I think I'd just like to end by saying that I'm really grateful to have been given this opportunity to speak at the IEEE Bangalore chapter, and best wishes for the next 50 years. And, I think a quote there for Ravi Kirloskar, that he illuminated Indian industry, not just with electric machines, but with quiet integrity, technical excellence, and a belief that engineering could build a stronger nation. So let's advance technology for humanity. Thank you.
On the 50th birthday of IEEE Bangalore Section, we had a glorious account of the 50+ years of wonderful academic and entrepreneurial journey of Professor Vijay Chandru. Let's put our hand again for a wonderful lecture.
Thank you. Sure.
So we have time for a few questions. So whoever wants to ask the question, please take the mic, announce your name, and finish the question in half a minute. Yes.
Thank you for a wonderful talk.
Thank you.
The question is, as a parent, what would you recommend for a young engineer studying biotech or biological engineering in an Indian university today? What should that person do? What can they do? What are the opportunities?
I think the world is their oyster, right? There is, I mean, it's incredible to be trained in biotechnology. I, would actually suggest they go a little further in studies, because, biotechnology and sort of interdisciplinary subjects are not foundational, right? So it would be important to pursue a little further and actually maybe at least a master's. So there is a little more understanding of what exactly excites them. And so that's just a thought. I mean, I always advise people against doing undergraduate in computer science, I would say do it in electrical engineering, or or if you want mathematics, but do it in some foundational subject and then move to.
Any other questions? Yes. Please announce your name, affiliation.
Yeah, thank you very much, Dr. Vijay Chandru, for the very insightful talk. My name is Swikrit, and I'm affiliated with this with IISc, the PCD program, actually, Brain Computation and Data Science. And
Right.
so, actually, I was wondering, now we're entering this era where, like, terabytes are really nothing anymore. We are going in much larger scales. And for, I think, safety critical applications, and when you're talking about, storing, let's say, genomes, and here, like, just you mess up a single letter by any chance, things can change completely. So I was just wondering, like, you'll be aware of Project Silica, and there are these techniques that are coming up to actually store data which cannot be corrupted in a particular way for a very long period of time. Have you, or do you know of any, like, are we doing this in the country to kind of make sure that?
I mean, there's Pratati is here, Genome India project, and they're storing the data from 10,000 genomes. There might also be, it might also make sense to store the biological samples and not just worry about the data, because at least DNA is stable for at least 500 years. So you can generate the data on demand. And there's a good case, because the costs are coming down, to not worry so much about doing all the sequencing now. Wait and do it at the right time. I remember when Aadhaar was being created, there was this great argument that deduplication was too hard, right? And people said, these guys are attempting to do it for 1 billion people, they will fail, right? And I think it was Pramod Verma who made the argument. He said, we'll wait for Moore's law, right? And we'll figure it out. So let's not worry so much about it. We'll figure it out. So with some biological samples you can't store for that long. You can at minus 80 degrees for a while, but DNA is not a problem. DNA it remains quite stable. So that's one part of it. I'm not quite answering your question, but I think better technologies for making sure that there is no loss of integrity in the data is important. I think there is also all the other issues of data security, which now by law, because of the DPDP Act, we have to make sure that data is protected, privacy is protected. So we have to come up with all kinds of mechanisms for that. So I think there is, there's a lot of technology issues that, but there's sort of techno-legal issues as well, so it's also important at some point, I think, for this campus to get a little more aligned with the legal side. And again, I think Rahul Mathan is probably, he was the first author of the early versions of the Justice Sri Krishna report, which eventually became DPDP. So, and he's very friendly to this campus. So looking to the leaders to think about maybe starting a conversation around the techno-legal aspects of data and data security, right? But your point is well made. I think here, for example, sickle cell disease is just one flip of one character, right? So one flip of one character in 3 billion is a noise level that could well happen, right? And so you do have to be careful, right? Which also makes the bioinformatics related to genomics, you know, quite complicated because you're looking for needles in the haystack and they have to be found with high precision. So not only is there efficiency of algorithms involved, but also you cannot afford any lack of precision. So that's what was fun about building Strand was you had to pay attention to both issues.
So, yes.
Oh.
One last question.
Professor Vivekananda, IIT Bombay and IISc Thiruvananthapuram. Would like to place a question about what is your take on intervention of AI in early cancer detection?
Right. I didn't put up the slide because you know, I didn't want to advertise too much, but yeah, the current status of early detection of cancer, of course, you know, you have the standard clinical procedures of a colonoscopy, a mammograph, you know, mammograms and so on. And various types of CT scans for lung, for example. But from a blood sample, a blood test, about maybe 7-8 years ago, Strand introduced the first liquid biopsy tests, where we were actually looking for mutation markers, okay, tumor signal from the blood. And those are very dilute markers because you'll have, you know, lots of normal cells and a few tumor cells. And to pick up that signal is quite complex. Today, we are working with something called epigenetic markers or DNA methylation. And companies in the West, like Grail, Guardant, and so on, have claimed success, Exact Biosciences. Strand has a test. It's ready. It will be launched very soon. The article is being reviewed. So I think we're waiting for the publication to come out, and then the test will also be launched. From a 10 ml draw of blood and using methylation markers, there's lots of machine learning involved because, you know, right. So we've had to, you know, run thousands of samples in order to train the ML. But it's working, and the good thing is that it's getting very encouraging results on number of cancers, almost 14 or so, and picking up signal at stage 1, which is very important because that's the stage at which you want to detect for early detection and intervention. So something for India is coming soon, right? Is all that I have to say.
One last question.
I'm sorry, I will be very brief.
Sure.
I'm Professor Balasubramanian, retired professor from IIT Delhi.
Right.
And actually, you know, as a parent of our daughter, who is suffering from schizophrenia, which is actually, you know, the mental illness.
Right.
So we have been going through this since, you know, quite a few
Yeah.
years. I think, you know, many of these psychiatrists, they more or less, you know, we can say, you know, they are going by just trial and error kind of things, you know, and 1 or 2 drugs are very effective for many of the people suffering from schizophrenia and all that, mental illness.
Right.
But we are wondering, you know, whatever you are talking about,
Right.
this microbiology and, you know, the brain center, we are, I was particularly interested in this because, you know, because, you know, this is the
understand.
research center.
Right. No, I think maybe you should have an offline conversation. But the CBR is more focused on neurodegenerative disorders. not so much on mental health, but I think we can still.
It's a very, very
Yeah.
important area.
No, it is. Right. And, I think as far as treatments based on CRISPR and so on, right now, most of the CRISPR gene editing, gene therapy treatments are targeted at very clear Mendelian disorders. So you know exactly which is the gene and what is the mutation that drives that particular disorder. Then you can go in and intervene and, actually edit.
There
right?
are some effective medicines.
Medicines are there.
That is there, but we want to really,
Understand.
Okay, thank you.
Yeah.
Thank you.
Yeah. Thanks.
So that brings us to the conclusion of a most fascinating talk
Thank you.
by Professor Vijay Chandru, who has actually told us about some of the glorious shots that he has played during the first innings and also second innings, and more such strokes are in store for all of us. So for giving us such a wonderful lecture and a most befitting inaugural lecture of Ravi L. Kirloskar Public Lecture Series. Let's thank Professor Vijay Chandru.
So on behalf of IEEE Bangalore Section, we thank Dr. Chandru. We also thank Professor Narahari. Can both of you please be on the stage?
Oh.
So we have a small token of appreciation for Dr. Chandru, and we'll request Professor Narahari to do the honors, please. The first one.
Actually, started comparing Suryavanshi and
Yeah.
So this is a 50 years coin. We should also give it. A 50 years coin.
50 years coin.
Sure, thank you. Thank you so much. May I request Professor Hari to please felicitate Professor Narahari? Yeah, please come. Yeah, I'll do that. Yeah. Yes, of course. I'll do this.
Yeah.
Yes, and the other one. This is actually yours to find. This for you again. Thank you.
Without giving it
And we would like to invite Mr. Anand to the podium. We have a small token of appreciation from Bangalore Section to the Kirloskar family. Please, Mr. Anand. So Mr. Anand has been saying that he doesn't want to be on the stage and not speak, but we must do this. Thank you for being here and being observant for the entire session. So can we actually invite all of you, please come on the stage and please felicitate Professor Mr. Anand for this. Yes. So with this, we are coming to the closure of the session. So we will take a group picture. You need not move at all. Please be at your seat. So you want to probably say a few words on So we request all of you to just be seated, don't move, and we'll have the photograph taken from this side. Are they all coming? Just check it out. Can all of you be seated? Please have a quick seat, yes. Yeah, I'll be seated as well. So we'll just close with a small vote of thanks. If you could just be seated for one more minute. May I invite Dr. Chengappa to do the vote of thanks on behalf of Bangalore Section.
Respected dignitaries, distinguished guests, esteemed members of Kirloskar family, IEEE leaders, speaker, volunteers, and dear participants. As we come to the close of this memorable and historic evening, it is my privilege to propose the vote of thanks on behalf of IEEE Bangalore Section. As we have witnessed, today's gathering was not merely an event, but a meaningful beginning. The inaugural edition of IEEE Bangalore Section Ravi L. Kirloskar Public Lecture Series, launched as part of the Golden Jubilee celebrations of IEEE Bangalore Section. At the outset, I would like to express our heartfelt gratitude to the members of Kirloskar family for gracing the occasion and also supporting a platform that seeks to inspire generations through knowledge, innovation, leadership, and societal impact. Our sincere thanks to Mr. Vijay R. Kirloskar, Executive Chairman, Mrs. Meena Kirloskar, Vice Chairman, Ms. Janaki Kirloskar, CEO, Kirloskar Electric Co. Limited, Mr. Anand Hunur, Managing Director, Kirloskar Electric Co. Limited. Their presence and support today has added immense significance and warmth to this occasion. The values associated with the Kirloskar legacy, leadership with trust, nation building, pioneering spirit, and long-term societal commitment deeply resonate with the ethos of IEEE and the mission of advancing technology for humanity. We extend our profound gratitude to our distinguished speaker, Dr. Vijay Chandru from the Center of Brain Research, IISc, for delivering an inspiring and thought-provoking lecture on architecting impact at the confluence of math, machines, and medicine. Sir, your reflections beautifully demonstrated how interdisciplinary thinking, technology, and human-centered innovation can come together to create a transformative impact for the society. Thank you for sharing your insights, experience, and vision with all of us. We also sincerely thank Professor Y. Narahari, IEEE Fellow, for chairing this session and enriching the proceedings with his presence and guidance. A special note of appreciation for Professor KVS Hari for taking us through the reflections and the journey of IEEE Bangalore Section over the decades. As we celebrate 50 years of impact, innovation, and volunteerism, it is important to remember that leaders and volunteers who laid the foundation for this vibrant community we see today. We are also grateful to Jill Gostin, 2026 IEEE President-elect, for a special video message and wishes to IEEE Bangalore Section on this very milestone. My sincere thanks to Dr. Prashant Mishra, Chair of IEEE Bangalore Section 2026, for his leadership and his vision in steering section during the historic Golden Jubilee year. To all the past chairs, society chapter leaders, affinity groups, subsection representatives, student branch counselors, volunteers, members, and participants, thank you for being an integral part of this journey and for continuing to strengthen IEEE ecosystem across the state of Karnataka. No event becomes successful without the silent efforts of all our volunteers who are working tirelessly behind the scenes to every volunteer, organizing committee member, design team, logistic coordinators, technical support members, registration team, hospitality team, the team headed by Akram and Co, who are managing the AV support today, and also to the participants who are joined with us online. Thank you for your dedication, professionalism, spirit, and service. As we conclude today's program, let us carry forward the spirit of collaboration, innovation, and community that defines IEEE Bangalore Section. Thank you once again for everyone to joining us today and making this occasion truly memorable. Wishing IEEE Bangalore Section a very happy birthday, and very happy birthday to all of us. Thank you.
Thank you also for taking the legacy in the next as a challenge.
Thank you.
We close the proceedings. We have arranged for tea, coffee, snacks, refreshments on the other side. And let's network together and spend the next half an hour here. Thank you very much. Yes. Yes.